Thanks for inviting me. I'm located at Middle East Teknik University, Ankara, and I'm the director for Center for Robotics and AI there. Now, today we have listened to a really nice talk by Agnesh on human-robot interaction, and that's interesting. I'm kind of, I also have an ICAP, but I'm also approaching it in a different way. So I'll give you a sneak preview of basically what I'm going to talk about tomorrow, and then jump on to this, slightly, more, course-like content that I was asked to deliver you. Basically, when you look into the world of robotics, you see two kinds of robotics, okay? Like there are these robots, okay? Let's see if it's working. Okay, no, it was working, but it's not. Okay. So you get the idea. There are two different robots. Like, there are robots, okay, that look nice. And actually, I could put ICAB as well, okay? But they don't do any real work, okay? They're nice, you can hug them, they evoke emotions in you, okay? They're great for that, but you don't see anything doing with them because they're very fragile. You cannot run them with complex things and so on. Okay, and then there are robots which does work. Okay, this is a Universal Robots, collaborative robot platform. These guys work 24/7. Okay, they do really boring jobs. They are actually being deployed in hundreds of thousands across the world. And this doesn't look like, this is nice, doing no work. This is doing work, but it doesn't have any human-robot interaction skills. So I'm interested in how to basically make these guys come to alive while also doing work. That's the gist of my idea. And for this, as I said, I will, if my video works, okay, then I'll show you. Again. See if it works. Okay, good. So, and now it's, okay, good. Let's see. Good, okay. Now my motivation was in this line of work is that, when you look at these robotic manipulators and when you go to the actual, assembly lines, you see that whatever all those workers do in terms of manipulation is beyond what we can imagine to do with actual robots. Okay, so the best that we can do, and so for us is to aid the worker. There's this assembly worker, and in this case we have this scenario where my student is assembling an IKEA chair. So look at the manipulation tasks that he's doing. Okay, can this guy will do it? No. Will it be able to do it in the near future? No, okay? We have these nice hands, but you don't see them. When you go into the industrial side, you have these, jaw grippers. They sell it for quite a large amount of money. They just have 1 degree of freedom like that, okay? And as such, there's no way that you can do this unless you have some attached tools that's really specific for this. So the idea that we had was, instead of robots doing the work, why not, the robot work like an apprentice, that just to give the worker the tools and the parts, such that instead of this guy carrying out his work in 60 seconds, if you can make him do it in 50 seconds, then that's 20% gain right there, okay? So that's the idea. But when you do this, then this guy will be a companion, and he needs to have, be a little bit smart. He needs to understand how basically the human is basically doing the work. His state is looking at him because maybe he's doing it at his own pace. And he needs to have, really basic, nonverbal communication such that they can have some kind of a connection. So towards this, this is our kind of the trailer scenario. And I'll just show you one more video, and then I'll move on to the last thing, to my actual lecture today. That's planned today. which is here. Now, I want you to, again, good. Okay. So this is, this is the view that you see from your glasses. This is your first-person view, okay? Okay. So does it come alive? Huh? Okay. So what it's doing is it's tracking human. Okay, we have this motion captures, but you can do this. And then, we just have this, gazing. It doesn't have eyes, all those, these glasses, that's dummy, okay? It's my old, sunglasses that I attached there. But even if that, like you see eye cup, and as I said, it has these nice, basically eyes, which follows. But what you've seen was that directing the gripper to someone induces a gaze. You feel the gaze on you. And if you just make it kind of like this, then you just feel like so live and so kind of fluid. Then you get much better human-robot interaction than you would get with a nice thing. And with this, basically, what I will do is I will stop here, and then if you come for to my lecture tomorrow, then now I will move on to my actual lecture that's planned for today. Okay, which is this. Let's see if I can. Good. Yes. Okay. So I was asked, basically, I didn't realize that this was kind of like two different, phases, and I was asked to, no, why do we, why is it not showing up here? No. All technical. I don't know why. Now it's here. Okay. The projector problem, that's the MP complete problem that, that will never ever get solved in our lifetime. We have new connectors, new projectors, new interfaces. The problem still is there. It gets even more worse. So I will talk about, I will give you an introduction about these robotic manipulators, okay, which I'm working on. And in doing so, I was told that this audience was kind of more knowledge representation, basic background. So I'll try to be basic. So if you know it, it may bore you. If you don't know it, it may become difficult to you. So I know that I will never make all of you happy. I apologize for that in advance. But I'll just basically try my best to give you an idea, basically, what it is, what is required, the basic concepts of to do that. So that's, this one is the, I'll quit this. This is, it's the PDF that I'm trying to, it's here. Okay. Close the count. Yeah. Do it. Okay, perfect. Okay, thank you. So I'll give you a brief kind of lecture introduction of how to basically about robotic manipulators and introduce you some concepts. As I said, this may bore you some, and so as I said, ARM type robots. Okay, these are the real workhorses. Okay, for robotics, and that's actually the main success story that has been pushing all this robotics research. Okay. And its main consists of static base, comprised a series of rigid links, okay, and actuated joints, typically deployed in manipulation tasks such as welding, assembly, handling, where we need repetitive and precise and fast execution of tasks. And typically they operate in a very limited workspace, which is highly structured, just like this, welding, basically assembly line portion where there are no humans and everything is done and no human is present. And this is basically a phenomenal success. And when you look at this story, it's like the first basically industrial robot, like when we say ARM time robots, you can replace it with industrial robots that it's designed by Engelberger and DeWall. Like this is the first one that was made, okay, and it's a huge beast. And it's basically It was used at GM's, factories to unload finished casting process. It could carry something like 40 kilos. And it had used hydraulic actuation, and it could be programmed by demonstration. There are a lot of nice videos about this. Now, what do we have basically in these robotic manipulators? Well, first off, what do we mean by manipulation? Manipulation means, moving things in space, like moving an object, like pushing this, etc. Now, you can contrast this against navigation, which is in navigation, you move, okay? Whereas these guys don't move, but they move things. So that's what their job is. That's why we call them manipulators. And this is a commercial manipulator. You have a fixed base where you attach them. And after that, along with that, what you have is a series of rigid links which are then connected by joints, okay? And when we say joints, basically when you attach two rigid bodies to each other, which I'll tell you basically what it is, then these joints kind of limit their basically ability to orient or move with respect to each other, okay? And here you can see like all these red caps, each of them is a joint. Then these joints can be passive, okay? Like for a door hinge, for example, that's a joint, and we call this a revolute joint, or we can have this prismatic joints. There are other types of joints, but these are the most basic ones. In prismatic, you basically move along basically linearly as such. And in this particular one, it has six active actuated joints, which can be actuated by electric, pneumatic, or hydraulic. And it has an end effector. The end effector basically is where they manipulate, how the manipulator does things or manipulate things. This is typically what we focus on, and this is designed for the task at hand. It can be a jaw gripper, a three-finger gripper, a vacuum. It can be a welding tool, or it can be an actual hand, whatever you put in there. Usually our goal with these basically manipulators is you do the manipulation with this end effector, and the rest you're try to avoid things for any kind of collision. That's the basically game. Of course, like there are some exotic studies where you use the hand, the arm basically to push things, but usually we just stick with this end effector. And when you look at them, there's the different things. That there's the payload, which is how much it can carry. Okay, typically when you buy this arm, the end effector you buy it separately, so it also includes this hand, okay. And then there's this reach, the maximum distance a robot can reach within its envelope. Then there's this precision, meaning that how accurately a specified point you can reach, and repeatability, which is kind of related, but if you give the same commands, what's the probability that you will be ending up in the same, basically, you will be moving your end effector to the same point, okay? And the workspace depends on it. As I said, using this, typically, we have these, prismatic and revolute joints, and you can use them in different configurations to create different robots. This is, for example, like combining 3 prismatic joints, and this is called a gantry robot. And in this case, the workspace that you can reach here, so this one moves along here, then moves along up and here. This is like a crane that works in the docks, and you have this Cartesian space in which you can basically manipulate things. And then, for example, this is another one where you have a cylindrical base, and then you have basically 2 prismatic joints up there, and there you can have this cylindrical workspace where you can basically manipulate things. Or if you have like a spherical, design here as such, then this is your workspace and as such. So depending on the length of the length and the relative positioning of the links, and as well as the type of the joints, basically determines your workspace. And when we do work with them, we typically have different spaces. Okay. The first one is, like we see with the world reference frame, and I'll talk what we mean by this, which means that, sometimes when you have a task, meaning I want to reach to this point. This point has a coordinate, okay? And then it means that, when you talk about this world reference frame, you specify the task without taking into account of the robot, okay? Meaning that I want to go to this to space, and then basically I don't care about what the robot is or whether it can do that. And then there's this joint basically reference frame. The joint reference frame is basically, for example, consider this universal robot's arm that I have shown you. It has 6 actuated joints, meaning that, on all these joints that can rotate, just for the same, 0 to 2 pi, okay, all around. So it means that you have this 6 theta angles for the joints, and whatever you do, then you have to determine, you say that here's my current thetas, I want to have move to this robot here, and then you basically design that basically in that space. We will see that space can be handy in, for example, planning, which I will not get into, but maybe we'll discuss it as such. And then you can also have this tool reference frame, which is nice. If you just fixate the room, then it's much easier for you to work on. Now, when you have a manipulator, then you need to specify, okay, its configuration. Meaning that, I have this robot here, and how do you specify it? Well, there are many ways to do that, okay? One way is, I can look at all the points here on this, on this body, okay? Say X, Y, Z of all the points. I can put them into a list, okay? And that will define you what your current state of the robot is, what the current configuration is, okay? Now, so that's nice, but is it the best way? Not really, because if you move a bit, then you will only get a new representation. It will be a very dense representation. And regarding that, okay, we say that we'll try to basically find the minimum set of parameters that is sufficient to specify or describe the configuration with minimum terms, okay? In this case, for example, robot, we have these 6 joint values, which tells how much a link is rotated with respect to the previous one, with respect to the previous one. And that gives you 6 angular variables, which are all between 0 and 2 pi, and that is actually sufficient, okay? Because all the other things, such as the length of, or the length of the, for example, links, width, etc., everything you can derive from that, okay? Because they don't change it. So we call this the degree of freedom, and this is basically, in our case, in this robot, if we say that it has 6 degrees of freedom, and if they are all actuated, it means you can control basically your robot as such, okay, with 6 degrees of freedom. Now let's get a little bit, easy, meaning that working in 3D, okay, is slightly difficult to understand at times. So I prefer to go with a smaller 2D case, and some of my writings. These are from my hand notes, which I have scribbled. So if you can't read it, just raise your hand. Okay, it's my handwriting that's right here. So, for example, take this case where I have this revolute joint. Okay, and I think I also have this laser, right? Okay. So this is a 2D, basically simple robot where I have attached here, and then it has a length of L2, and then you can basically do that. Or this is a prismatic joint. You can say this top view that can go up and down. And we usually specify the configuration with Q. In this case, the Q is θ1 from this basically this plane. Whereas here it can be just D, which is the the translation that you do here. Or you can in both of these basically robots, they have 1 degree of freedom because you just have 1 control parameter. Okay. And now you can see here, for example, in this case, when I change theta, if I look into the task space, then you can see that the end effector position, xy, I'm changing 2 things at once, right? But these x and y's of this end effector are not independent. I cannot change this x and y as I wish because I'm subject to this specific thing. So, but with theta, you can give anything. Of course, like I have this base here, so you can go between 0 and 2, with 0 and pi, but 0 and pi will then leave you this x and y coordinates of this end effector, okay? The same thing is here. Now we can have basically more complex manipulators. Like in this case, I have a prismatic joint followed by a revolute joint here. And so in this case, it has a 2 degree of freedom because it can go on up and this can then turn around. Whereas I can have like a 2, for example, revolute joints as such. And in this case, I can define as, we call this 2 degrees of freedom. Now, based on this, you can see that the world that you can reach are determined by this, right? Okay, so this robot, I can reach to points here, whereas all the other parts, I cannot reach them. Or for this prismatic one, I can only go up and down. Whereas here, it can go up and down, and then so it looks like this, okay? Whereas, if it's like these 2 revolute joints as such, then it's slightly more complicated. Now, how do we, now, one question, as I said, when you want to manipulate things, then you need to, typically you have an object, okay, that is sitting somewhere in the space, okay, in the world, and you want to say just touch it, okay, that's usually the first thing that you want to do. But if you want to touch this, then you need to understand, well, I mean, like, I cannot just tell the robot to go and touch because I have this, say, 2 or 3. I have to find what these theta values are, d values. I have to compute them. Okay? There is a mapping between those, those degrees of freedom that I can control and the actual world. So that transformation, I need to model that, and that's basically the gist of what I'm going to tell you here. So here, for example, like say that I have this simple, 1 degree of freedom here. And so, and then assume that like this, I put this robot here, somewhere here, say on this desk, and here's an object. Now, where's the robot base with respect to the world? Maybe, I'm computing the world with a coordinate frame from that corner, okay? So I need to know where my robot is. Okay, where's the end effector with respect to my base? I know this, okay? Where's the object with respect to the end effector? Okay, and then what should theta be to get the end effector closest to the object? Okay, so these are all things that I should, try to figure out. That's basically, the problem that we have here. Now, as I said, we already know basically this, like, we have basically, come up with this, Cartesian coordinate system, right? It's basically we have defined a coordinate frame, okay? It's essentially a set of axes that intersect at a point here. In this case, like I said, I put this like with O here, X and Y, and I have these actually are unit vectors, okay, along these axes. They don't have to be orthogonal, but, usually we prefer orthogonal, but they don't have to be. And with this, once you put a coordinate frame, say to one corner of your space, then, and if I have a rigid body, when I say a rigid body is something that's deformable, like anything that's kind of a solid is a rigid body, okay? If you can stretch it, then it's not. And so if I want to represent this state, for example, as I said, I can just put like any point here, like within this coordinate frame, I can specify with these 2 coordinates, x and y, okay? What this means is, like this x and y means, if I have, say, x1 of this x unit vector, remember I have a unit vector here, so when I say x1 here, it means x1 copy of this plus y1 copy of this, okay? And then you combine them, and then it will lead you to a point, and that's where your point is. Okay, that's what we do. Now, if you have a rigid body, then you have many such points, right? But this is a redundant representation because, in a rigid body, what I also know that I can have all these things, but any points that I pick, Pi and Pj, the distance among them should remain constant. Okay, this is what the definition is. So it means that, when you select these points, they cannot take arbitrary values. Rather, if you move this rigid body here, still they are subject to get to this. Okay, that's the idea. And so if I have a rigid body in 2D, I can represent its configuration with how many parameters? No? 3. 2 for position and 1 for orientation, right? Okay, so it means that in 2D, you need to have 3 parameters at minimum, okay, to basically represent that. And so we call this, and so it's not just for 2D, but also 3D, as the pose. When I say pose, it means position plus the orientation, okay? And in 2D, the pose is basically 3. In 3D, a rigid body, this pose can be specified with 6 numbers. X, Y, Z, which is the position, plus angles along these axes, rotations, okay, along X, along Y, and along Z, which we call Euler angles, okay? So with this, now, coming back to our problem, that, this is my world, and I have put a world coordinate frame with O here, okay? And then I can now, instead of basically keeping track of these things, I can attach, remember I can just have a post-it. I can just attach these coordinate frames wherever I wish, okay? So I will say attach a blue one called A to this basically revolute joints to make things easier, okay? If you place your coordinate frames nicely, it will make the math easier, okay? If you don't, you will still get the correct answer, but the math will look ugly, okay? And then I put another one here. And now within this, and let's say that I have an object here, okay? And now what I need to do is, I have this 3 coordinate frames, and I have an object. And what I want to do is, I want to find out, what's basically the relative pose of this blue frame with respect to the red frame, okay? And then now that's easy, right? There's a translation. And then, what's the relative pose of this green one with respect to this blue one? That's also easy, right? And then, what about this object within this green frame? That also looks easy, okay? Now, within this, if I have, you can see that I can hop from here to here, then if somebody gives me this object's location in space, okay, which is here, okay, then I can find out what this object means in here, okay? So let's see how we can do that. Now, I just simplified things here I have basically 3 coordinate frames, O, A, and B, okay? And let's pick a point. When you pick a point, say P, this is the same point, okay? Now, this P will have different representations in different coordinate frames. For example, in this world coordinate frame here, P, it's 3 of XO, so I have an XO here, 1, 2, 3, okay? And then, 1 and 2, and then it has 3 Y0 component, 1, 2, 3, okay? So it's basically I say that since I have this P represented in different coordinate frames, I need to basically make them visible. So I say it's a P, position of P, point P in coordinate frame 0, O, okay? Now, I can also do the same thing with A. In this coordinate frame, for example, the same point, P, I will represent it as -1 and 1, Okay? In x, it will be -1. In y, it will be +1. Okay? Whereas in b, it will be 1 and -1. Remember, I'm representing the very same point. I'm just changing using them as such. Okay? And these numbers, again, so this letters here, the letters here, tell me which coordinate frame that I'm using. Are you still with me? I'm trying to keep things as simple. I know some of you may be bored, but just bear with me. Okay? Now, with that, now I need to define a transformation from them, meaning that, okay, if I know, say, the representation of P in one coordinate frame, can I compute it in a different frame? Okay? So if I know it, for example, like from my end effector point, so that I have a camera, I know where the object is, can I compute the position of the object in the world coordinate frame? Which is difficult, right? That's the goal. So I will define this, I will define a transformation, say that, remember I have these 3 coordinate frames, and in here, I will define this, for example, TAO means it's the pose of A, this coordinate frame, in coordinate frame 0, O. Okay? Now, in this case, you can see it here. Remember, P is the same point, right? In here, I would say that PO is this vector, okay? Whereas PA is this vector, this blue one. Now, from this, you can see that PO, okay, is actually the translation of the center from here to here, which is I call this translation of A in coordinate frame O plus PA. Okay? So I'm just like a PO equals translation plus PA. Okay, and this will hold true for any basically point representation in space. Okay, simple enough, right? So I will so this is the simplest case for basically this transformation. Nice. So if it's just translation, it's easy. Like I had my coordinate frame at the corner. Now I put my new one here. I just measure the translation, and then if I get this here, I just have to add this vector, and I'll get that. So this gives me that. Now, what about, let's see, for example, in this particular example, remember that this one was 3, 2, this one was -2, so for example, like with PA, it will be 4 and 1. That's the translation of basically A with respect to O here. Okay, in X, it's the translation. Then comes rotation. Okay, now rotation is all ugly. Okay, this is just 2D. If I show you 3D, it's even uglier, so I'm not going to even bother to get into that. But here, let's say that, I'm just simplifying case. I have 2 frames that are called their, basically, coordinate, basically, the intersection points are the same, okay? Here's the red one, okay, with O, and then there's the green one, and I call this B, okay? And these are the vectors, so this is the unit vectors. This is, XO unit vector, meaning that its length is 1, okay? And then it's here, and then here's my XB and YB, so you can see it's rotated a bit, okay? Now, let's look at this again. How am I going to represent P, right? That was the same thing that I had done in the translation. In this case, the P0 will be like this, PB will be like that. They will be right on top of each other. So what we used in the translation case is not working, obviously. Okay? Whenever we do that. Now, note that, okay, for example, for this P point, when I say it's 3, 2, okay, so it's 3, it means that I'm actually multiplying this with this unit vectors, meaning that I'm having this is kind of like, you remember this math, vectors and matrix multiplication, right? So this x0, okay, replace this with this vector. So I'm multiplying 3 times x0 plus 2 times y0, right? This is kind of like implicit in my representation. Whereas in PB, it will be like, remember that this is going this way, it will be 4 and 0. So it will be basically 4 times xp plus a 0 times yb. So that's my PB representation. Now with that, what you can do, which I'll skip, is if you have a rotation of theta in between, okay, given this, if you write xb, okay, in terms of, say, x0, which you can do here by using something called dot product, okay? A dot product of two vectors is essentially the projection, the perpendicular projection of that vector along that axis. And in this particular case, basically, what you do is you say that there xb, for example, here, in here, xp, I can write it in terms of x0. xp is, if this is theta, cosine theta times x0 plus sine theta times y0, okay? And you can also do it for yb, okay? Once you do that, and then if you plug this here, then you can get a, basically, representation for, basically, that equation that's linking the PA and P0, okay? And then you can get this, basically, matrix, which we call a rotation matrix, okay? This rotation matrix is actually a 2 by 2 matrix, okay? And what it does is, it has this form. And in this particular case, when I have B, like we call this the rotation matrix, rotation of frame B in frame O, okay? And we say that this is theta. Why, like how do we do that? It's because, in coordinate frames, we have this right-hand rule. Meaning that if this is my x direction, y direction should be in my right hand, should be in this here, okay? It's not this way. It's always right-handed, okay? And when I do this basically rotation, it's in this right-hand direction. So that's theta. And then, this basically this matrix is, cosine theta minus sine theta, and cosine theta. So this is a 2 by 2 matrix. And if you multiply basically PB with this rotation matrix, you'll get a representation of that in PO. And you can see, like, if you noted that, this representation is nice, this notation is nice, that, you just cancel this, okay? Multiply, and then you get PO, okay? So this rotation matrix, as you can see, it has 4 components, right? Like, but it's determined by just one thing, which is theta. Meaning that you cannot have, like, cannot just say, 1, 2, 3, 4, like a matrix, and expect that this is a rotation matrix. A rotation matrix has to satisfy some constraints. And it's actually, these values that's represented by different values of theta, it is actually, it's this, we call this special orthogonal, basically space, and the R is orthonormal, meaning that, the length of basically rows and columns are 1, and that they are perpendicular to each other, okay? We call this orthonormal, and one basically interesting property of this is that the inverse of this matrix is equivalent to its transpose, okay? Now, with this, I have now shown you, how I can transform between coordinate frames for translation and for rotation, okay? So given this, okay, so for example, in here, like what if I have a case where, I am both, translating and rotating, okay, both of them at once? Well, it's easy. You first translate, for example, I say, PO here, okay, is translation of A with respect to O plus, PA times the rotation of A with respect to O, okay? So I translate it and then I rotate it. That's fine. Now with this, I can write them as such, like this point 0, let's say that xy is the translation, here's the rotation matrix, and here's the representation in frame A. Now, this looks good, but it's a little bit ugly, meaning that, if I go through this with once more, like if I, from A, if I want to go to B, then, well, it will get uglier, okay? Now, to keep the mathematics simple, okay, what I can do is this nice trick of moving into homogeneous coordinates. The idea is, I was representing my point with just x and y, right? And if I just put an extra dummy 1 here, then, here, I can do the same computation, which is the addition and multiplication followed by an addition, with just one matrix multiplication here. So now look at here, x equals tx plus multiplication of this with the here. In here, x0 is, here's my second point here, PA, with also a 1 here. So you multiply this with here, the same, plus tx. The second line is the same. The last line, well, that's dummy, it's here. Now, why do I prefer this? I prefer this, but now, because if I have multiple transformations between multiple consecutive frames, like from 0 to A to B, all I have to do is matrix multiplications all the way, okay? Which is easier instead of going through like addition and then rotation and then followed by addition, okay? So this is much simpler. So I use this like sometimes with the tilde to say that it's actually in one extra dimension here. And we do this as, capital T, so P of A here, transformation of A in O, you get P of O, okay? What about the reverse? It's easy. P of A is inverse of this. I can multiply it with P O. That's it. So you get that. Okay. So with this, now remember that I'm trying to reach this object here. I can have these transformation matrices. Okay, meaning that if I put my manipulator here in the world, and once I compute this transformation matrix, I'm done, okay? I can go back between my robot base coordinates and world coordinates easily by just multiplying through a matrix. And the same thing, like from my robot base to the end effector. And then from here to that. So then I can define this. This is the transformation matrix of A in coordinate frame O. This one is transformation of B in A, which is easy. And then if you multiply them together, which is transformation of B in O is you multiply this with that. So you can say these cancel, these A cancel each other, and you get that. And what about the reverse? Like, A to B is B to A is inverse. You just have to take a matrix inversion, okay? Now with this, so that's the 2D one. In 3D, things get a little bit more ugly, okay? But the same idea works. Like in 3D, we have X, Y, and Z. And again, with this right-hand coordinate system means that you put your hand on X, you roll towards Y, and your thumb points to Z. Okay, that's why we call this right hand. And in here, now we will have our rotation matrix is 3 by 3. Okay? And then now we can define these rotations. Like for example, I can talk about rotation about Z. So when I do a rotation about Z here, so say with a gamma here, you can see that in Z nothing changes because I'm rotating around about Z. But X and Y changes. So X becomes X prime and Y becomes Y prime, and then here's the gamma. So, and here is the rotation matrix that I have here. And you can see that the Z coordinate here doesn't change, but X and Y changes, which is what I expected, right? And rotation about Y, again, this is around Y. So you can see that it's rotating with this beta, and then Z moves that. And this is my RY and rotation about Z, okay? Now, there is, when you have a rotation is not just about these axes, but on some arbitrary axis, right? There's this Euler's theorem, which says that any rotation in 3D can be represented by at most 3 rotations about axis, okay, such that no two consecutive rotations are about the same axis. Meaning that, you can recall this like, it can be, say, X, Y, Z, meaning that I can turn, so a rotation can be represented, by these different ones. But it cannot be X, X, Y, because X and X, then you lose kind of like, you need to have basically these 3 components. Or it can be X, Y, X. So there are a lot of, I think there are 24 different combinations of this. So and there is basically no one fixed way to do this, okay? Now, given this, now I'll go back to our, basically, remember we were trying to control a robot, okay? And now, you may have heard about kinematics. Kinematics is actually, it's the study of that which describes the motion of the manipulator without considering the forces or torques causing the motion based on the geometry of the manipulator. Meaning that, okay, if I get, remember that, I want to make my manipulator's end effector reach to a point in space, right? So, and if I know my link lengths and the type of joints here, then if I have, say, 30 degrees here, 60 degrees here, then geometrically I can compute where my end effector will be. That's basically what I mean by kinematics. I'm not talking about, it's just pure geometry. There's no force, there's no acceleration. It's just out of geometry that you have to do this. So we have 2 things. We have forward kinematics. In forward kinematics, the idea is here. You get these configurations, say in my UR, I have, 6 theta values, theta 1, theta 2 to theta 6. Given these, what's the X, Y, Z of my tool end effector? Okay, that's forward kinematics. And then there's inverse kinematics. Inverse kinematics is the following. Given X, Y, Z, given that I'm going to touch here, find me what theta 1, theta 2, theta 6 should be. Okay? So they are both useful, as we will see. How am I doing with time?
3 minutes.
Holy cow. Okay, that's what I was afraid. Okay. Okay. Let me just do this and then you'll get it. Okay. So for example, let's take this, for planar elbow, like I have this, L1, this length, like here's the L2, okay? And I have 2 revolute joints. So basically the forward kinematics takes theta 1 and theta 2. So you can say I've defined theta 2 with respect to theta 1, okay? And get the xy of this end effector. Whereas inverse kinematics is given xy, find theta 1, theta 2. Okay, they're kind of inverse mappings that we have to do. Now, how does it look like? Well, computing this, you can do it with these frames, right? We have learned about this transformation, and it's easy. So, what I have to do is, I've attached these coordinate frames here, so one here, and one here, okay? So now I can write this T1 in 0, okay? And this transformation is T2 in 1, okay? They both have rotation matrix and translation, and this is 0s and 1. Now this one is easy, right? In this case, this first frame is rotated by theta. So I just put this. And then what about this, translation? The translation is in L1 times cosine, C theta 1 is cosine theta 1. Okay, just shorthand. So this is L1 times cosine theta 1 and L1 times sine theta 1. Okay, again, easy. So this is, what about this one? That's also easy, right? With respect to frame 1, coordinate frame, what about the coordinate frame 2? Again, here's my rotation matrix. Looks complicated, but it's easy. And then this is again L2 cosine 2 and L2 as sine theta 1. Okay, that's it. And given this, I know that if I multiply this with that, I will get T2 to 0, which gives the end, basically end effector's position. And then if you just multiply this, then you'll get this. And bingo, this is your forward kinematics. Okay? As simple as that. So let me just go, I'll skip this. Maybe I'll okay. What about inverse kinematics? Inverse kinematics, you can see that, let me just go back here. So in here, like, this is my, like, since I know L1, I know theta 1, I can compute this. What about inverse kinematics? So in inverse kinematics, I said this should be, say, 1 and 2. I know the desired xy. Then 1 and 2, like 1, 2, and then you have to equate them to here. Okay? And, okay, from that, then you have to solve for this theta 1. By the way, theta 1, 2 means theta 1 plus theta 2. Okay? And here, basically, you have to solve this ugly set of equations, which is tricky, which can be tricky. Even in this case, for example, if I want to reach this point, I can go this way, or I can go this way. Okay? It has two solutions. Okay? And for some, you don't have a solution. Okay? So that's the idea. And the last thing, I'm running out of time. Okay. Well, blah, 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 blah. Okay. Blah, blah, and then thanks.